Welcome everybody to our Atto Fridays talk. Our speaker today is Dr. Kathryn Hamilton. She is now actually, or she will take up a position as an assistant professor of physics at the University of Colorado at Denver this autumn, but right now she is a postdoctoral research scholar at Drake University in Des Moines, Iowa, where she works alongside Professor Klaus Bartschat on applying our matrix methods to treat a variety of atomic physics problems. She obtained her PhD in 2019 under the supervision of Dr. Andrew Brown and Professor Hugo van der Haat at Queen's University, Belfast, with a thesis entitled R Matrix Calculations for Ultrafast Two-Color Spectroscopy of Noble Gas Atoms. The current research focuses on observing and controlling multi-electron dynamics in atoms exposed to external laser fields and electron collisions with atomic species. And when she's not running code on supercomputers all over the world, she likes to play traditional Irish music and domesticate feral cats, and both activities produce very similar sounds. I personally am not experienced with Irish folk music, but yeah, I have some experience with feral cats, so I can assure you that the sound is a bit...
it's not good.
No, but we can live with that. And so welcome, and we are ready to go if you are.
Brilliant. So thank you very much, everyone, for inviting me to present some of my research on the Atto Fridays webinar. I think it's a great resource to have for the Attosecond community, and I hope it has a very long lifetime. My presentation today is entitled Attosecond Photoionization Delays in Noble Gas Atoms. So even since finishing my PhD, I haven't quite moved away from the noble gases yet, but there's a variety of very interesting things to study there, so I'm sure you will forgive me. So just a quick overview of my presentation today. I'm going to briefly introduce the concept of a photoionization delay and chat about how we would measure this. I will introduce the RMT method, the R matrix of time dependence method. So this is for the calculations that I have carried out in support of the two projects I'm going to show. So these are two different variations of the RABBITT technique to measure photoionization delays. The first one's called threshold RABBITT, and the second is multi-sideband RABBITT, and these are performed with a neon target and an argon target. Finally, just as part of my conclusions, I will show you a brief demonstration of the Atomic, Molecular and Optical Sciences Gateway. So this is a fantastic web portal which contains some of the best AMOS codes throughout the world, and you are free to log on and use those codes through a convenient web interface. So first of all, when we chat about attosecond photoionization delays, what do we mean? Or what is our goal? Well, our goal here is to observe electron behavior on the natural timescale it occurs on. And this is the attosecond timescale. And processes which occur in this timescale are things like excitation, electronic transitions, and ionization. And our focus today is on trying to observe ionization in atomic species. And when we want to observe photoionization or put some kind of time scale on the process, what we actually observe is a delay. We can't really measure time directly, experimentally. So what we have to have is some kind of reference. And depending on whether you're a scattering person or more of an optical scientist, you can approach this idea of a photoionization delay in two sort of different ways. Really what we do is we measure the phase shift between our wave packet that has come through a potential compared with some reference wave packet. So in scattering theory, this would be an electron scattered from an atom, and we will compare its wave packet to an unperturbed electron of the same final kinetic energy. Optical theorists, you can think of this more as analogous to the group delay. And this is called the Eisenbud-Wigner-Smith delay, or I will refer to it as the Wigner delay, just to be short. And this is the energy derivative of the phase difference here, this delta E, that will give us our time delay. And some of the references that I have down at the bottom, the last two, give a more in-depth discussion of this idea and some of its problems. And one problem is this Wigner delay always an appropriate measure of photoionization delay? And the answer, unfortunately, is no. So because this depends on some sort of phase difference between a reference wave packet and the wave packet we're interested in, we need to make sure that our reference is always undisturbed. And as we approach things such as the tunneling regime, or we have auto-ionizing states, our wave packet becomes disturbed in a way that we can't really map, say, the maximum before this filter, either the tunnel or the auto-ionizing state, to the maximum after. So we have no correct way really to determine this reference, this phase shift. But for the problems I'm going to present today, when we talk about the photoionization delay, we mean this Wigner delay. And there are two different quite common ways to calculate photoionization delays. We can use Attosecond streaking or the RABBITT method. And another probably topic for a quantum battle is how does one spell RABBITT? Here I've put the acronym out in full. So RABBITT stands for reconstruction of attosecond beating by interference of two photon transitions. And at its core, RABBITT is simply a pump probe experiment. So we have an attosecond pulse train and an IR pulse. And the attosecond pulse train is composed of odd harmonics of the IR. So each consecutive harmonics are separated by twice the IR photon energy. And our attosecond pulse train is usually chosen so that the lowest harmonic is still energetic enough to ionize our target system. We introduce a time delay then between our APT and our IR pulse. And this time delay between the XUV and IR lets us build up, in a sense, a time-ordered picture of the dynamics. So we perform these calculations or take these measurements for different time delays between our two pulses, and we stitch the photoelectron spectra together, and what we get is this nice colorful final RABBITT spectrum. And in our RABBITT spectrum, you'll notice between our harmonic lines, we have these bright dots. And to get to this final photoelectron kinetic energy, we can follow two different pathways. One with the absorption of an IR photon and one with the emission of an IR photon. So for this final state, there are two different pathways. These pathways interfere, okay, so we have a difference between the constructive and destructive interference depending on the time delay, and build up these oscillatory sidebands. And our sidebands can be fitted to a cosine of twice our IR frequency multiplied by this time delay, plus a delta phi, plus a phase term. And the phase term can be broken down into several components. So first of all, there is a component from the group delay or the spectral phase of our attosecond pulse train. So this is unfortunately something intrinsic to the measurement. And then an atomic phase. And our atomic phase we can break down even further into this Wigner phase, which we can then convert to a delay, so our attosecond photoionization delay, and this continuum coupling. And this arises due to the absorption of the IR photons in the continuum, and unfortunately it's another thing that's sort of intrinsic to the measurement process. So often when we perform these RABBITT experiments, we need to measure, say, the difference between two different RABBITT phases, so we can cancel out things like the spectral phase or the phi CC, unless we know or can calculate those beforehand. And the method I want to use to generate these RABBITT scans is a computational method. It's called the R matrix of time dependence method. And the goal of RMT is simply to solve the time-dependent multi-electron Schrodinger equation. From that, we get our wave function. And from our wave function, we can extract our observables. So in this case, the photoelectron spectrum. And RMT seeks to do this in the most efficient way possible, where we include all our multi-electron effects where they're really necessary, and then try to simplify our problem so that we can scale up to maybe longer wavelengths or more difficult problems in a computationally effective way. So to this end, we employ the R matrix paradigm, just of the division of configuration space. So this results in a small complex inner region. Here we have we take account, of the dynamics of all our n+1 electrons, and we have all our resultant multi-electron effects. And then once we have one single electron that's separated far enough from the nucleus, we say this is in the outer region. And it's far enough separated that exchange no longer has to be taken account of. This electron is distinguishable. So we have this simplified single electron problem in the outer region, and we use then instead some long-range potentials to describe resulting behaviors. Because we have these two different really setups in our two different regions, it makes sense to use two different numerical techniques. So in our inner region, we have a B-spline basis. This is really sort of our matrix vector multiplication region, where we have all of our n+1 electrons. In our outer region, where we only really interested, our time dependence comes through from the radial wave function of our ejected electron. It's very convenient to cast this on something like a finite difference grid, so it makes extension of the outer region very simple to achieve. And one important question I think to answer is, why would we want to use something like RMT to study photoionization? Well, first of all, it is a fully ab initio method that can treat multi-electron effects. And while there are other methods out there, which of course can be appropriate to study this kind of thing, the thing about multi-electron effects, I feel, is that you don't really know if they're important or not unless you actually perform a calculation where they are included. So I don't think, we probably won't get anything too surprising arising, but one can't really say for definite unless you explicitly account for these things, as you do in RMT. And to that end, we want to see throughout these different projects, does RMT offer the best chance at comparison with experimental data? So we're very lucky to have experimental collaborators that we can compare with in the projects I'm going to show you. RMT is also appropriate for the entire breadth of ultrafast physics. So I won't show this today, but we have used it for strong field applications. It's been used for frustrated tunnel ionization and high harmonic generation. And then today we're also going to use it for things like single photon ionization as well. So it's a very multi-purpose code. It was also designed with high performance computing in mind. So it's parallel, it can run across many nodes on different machines. And it's also then scalable to these larger problems I talked about. Another really great benefit is the active development community. So the code is available on GitLab. I will have the link later on in the presentation, so you can go and download and try the code for yourself. But there are some people working very hard, mostly at Queen's University in Belfast, adding new improvements to the code continuously, so you can take advantage of those immediately. On the topic of recent improvements, so since its incarnation, I believe in 2011, RMT has made a lot of progress in the kind of things it can be used for, especially from about 2018 onwards. So the first step was to remove the restriction of only using linearly polarized light. So now RMT can tackle problems with arbitrarily polarized light fields. So this, of course, when we have arbitrarily polarized light, we break a lot of the symmetry in our problems. So these can be really, really big problems. We also now have the ability to look at semi-relativistic effects due to the inclusion of the R matrix 1 code as a generator of the input data for a subsequent RMT calculation. So things like spin-orbit interaction can be studied in a time delay dependent manner with RMT. We also can look at electronic behavior in molecular targets with another interface with the UK-AMOR plus code 2. And I couldn't show absolutely everybody. So I showed the sort of executive committee for the UK-AMOR team. So UK-AMOR is the consortium that sort of oversees the allocation of Archer time towards people who want to use the associate R matrix codes, and kind of mostly comprises of the developers of RMT as well. So the main person on the RMT end then will be Dr. Andrew Brown at Queen's University Belfast. And also, of course, Professor Hugo van der Hart, and wonderful people like Jack Ragg, Greg Armstrong, and Daniel Clark. Zdenek Mashin and Jakub Benda. I think I've got most of the main people who've been doing a lot of the fantastic work with RMT over the last while. So on to our first set of results. So our first project is studying attosecond time delays near the photoionization threshold of neon. And for this particular study, we use a variation on the RABBITT technique called threshold RABBITT. And here what we have done is we have reduced the energy of the lowest attosecond pulse train harmonic to now be less than the ionization energy of our target gas, so of neon. So in our RABBITT spectrum, the first thing we see, our lowest energy feature, is now a sideband and not a harmonic line. So more specifically for neon, first of all, we'll look at a pulse with a fundamental wavelength of 800 nanometers. So you can see that our lowest harmonic, the 13th harmonic, will be roughly resonant with this 2p5 3D state. And then when we absorb one more IR photon, we make the transition into the continuum. And why would we want to do this? Well, our whole goal here is to compare the atomic delay, which we discussed its relation to the RABBITT phase before, from this first sideband, so the one where we have a bound step and then a bound continuum step in our generation of our sideband, and see, is it fundamentally different in some way to the atomic delay obtained from the sidebands generated only above threshold. So they all have bound continuum XUV transitions. And we are going to do this, and we are really going to overkill this problem. We're going to throw everything we've got at it. We're going to compare experimental results with 3 different theoretical approaches. So we'll have a single active electron approach, we'll have perturbation theory, and of course our RMT calculations as well. So the experimental team, and really the people in charge of this whole project, are Matteo Moioli and Giuseppe Sansone at the University of Freiburg. So Matteo is the PhD student on the project, so he carries most of the burden in keeping us all correct. So I wanted to give a shout out to them. Their experimental setup at the University of Freiburg and originally at the Politecnico di Milano is incredibly impressive. I had a very brief career as an experimentalist, so I definitely won't do my description justice, but what I really would want to point out is the fantastic stability of their setup. So having only a drift of 40 attoseconds over a 54-hour acquisition time is, I can't even think what the percentage would be off the top of my head. It's incredibly small. So it's a very impressive experimental setup. Our perturbation theory team, these calculations are mostly headed up by Elena Gryzlova at Lomonosov Moscow State University and Maria Popova, who's the PhD student on the project as well. And for the perturbation theory calculations, we need to use third order corrections to appropriately describe the oscillations in the main harmonic lines in our RABBITT spectrum. And we also use a semi-relativistic version of perturbation theory. So our matrix elements are computed by the semi-relativistic version of the baseline R matrix code. And these calculations, even though they're semi-relativistic, they are very economical, especially compared to the RMT calculations. So we can do things like change our wavelength quite easily. We can do many delays. So these are very nice to aid in the interpretation of our results. The single active electron calculations, of course, were headed up by Klaus Bartscha at Drake University. And the calculations themselves are mostly carried out by our, at the time, 2 undergraduate research students. David Attry is now a PhD student at Stanford, and Gavin Manning is now a PhD student at the University of Minnesota. So in the single active electron approach, we only really take into explicitly account for, say, the dynamics of one single electron, and then a local potential captures the influence of all the other electrons in our target atom. And these calculations are non-relativistic, and again, like the perturbation theory calculations, they're very economical to do. So the code is parallelized over a single node, which is usually sufficient for the size of calculations we want to do. And so these are also very useful in fine-tuning our laser parameters that we wanted to use. Finally, I've already described our RMT calculations, just to point out that these are also non-relativistic as well. These ones were computationally more expensive than perturbation theory or single active electron. They typically took about 300 to 400 cores for approximately 2 hours per time delay. And then depending on how many time delays you need for each laser wavelength, things can scale up quite quickly, but on the whole, they were not the most intense calculations they've ever performed. So what do we see? Well, for our 800 nanometer wavelength, here I have the RABBITT scans from experiment, RMT, single active electron, and perturbation theory. And just as a reminder, what we want to do is to compare the phase or the phase difference in these the highest sidebands with the one sideband generated just above threshold. So I've put in the little pink line to kind of guide your eye. And especially in RMT and the experiment, you can see between the first and second sidebands, we have a phase shift of almost pi radians. And our very sort of rudimentary analysis, we can plot the oscillations in those sidebands, RMT and experiment. So the red is our threshold sideband, the blue is our next highest, our first real continuum sideband, and you can see indeed it is roughly a jump of pi between those two. Of course, we can do a bit more sophisticated analysis, and what we can do for each energy point, we can take the Fourier transform and look at the phase of the component oscillating at 2 omega, and then we can convert that phase to a time delay. So this is on our y-axis. And when Matteo first sent me this plot, I nearly had a heart attack because it looks like an absolute mess before realizing that most of this is actually noise. So the only place we expect an oscillation at 2 omega is indeed within the sidebands. So it only really makes sense to look at the time delay within those specific energy ranges. And when we do, we can see for the continuum only sidebands, we have really fantastic agreement between the experiment, RMT, and perturbation theory. I think anybody would be happy with this kind of comparison. When we get down though to our threshold sideband, things look a little bit different. So RMT seems to come the closest to describing the delay in experiment, but it's still about between 150 to 200 attoseconds off. We do get the same kind of increasing behavior in the delay across this sideband. Perturbation theory doesn't perform quite as well, and this is something we are still trying to look into more deeply. So this will obviously be very sensitive to the atomic structure, and we maybe made the mistake of changing too many things. So our perturbation theory calculations are semi-relativistic, our RMT ones are non-relativistic. So perhaps we should change that and see if we can figure out, a more concrete, quantifiable difference between the two. But we're very happy with this part of our result anyway. Next thing we did was we changed our central wavelength. So away from 800 nanometers onto 1006.4 nanometers. And we repeat our RABBITT scans. And again, we want to compare the phase between these higher sidebands with our threshold sideband here. And what you can see in probably easiest in the perturbation theory results is our threshold sideband now has a new feature. So now we have a kind of double peak here. And if we zoom in on the experimental results and on the RMT results, we can indeed see that we now have 2 bumps in our first sideband. So where does this come from? Well, when we change our wavelength, our XUV pulse is sufficiently short in time that it's broad enough in energy to populate both the 2p5 6s and the 2p5 4d. So we have contributions from both of those states appearing in our threshold sideband. And our experimentalists had such fantastic resolution, they even noticed something coming from the 5s as well, and the splitting between these states too. So we wouldn't be able to see the splitting in our RMT calculations because they are non-relativistic. We repeated our 1006.4 calculations at a lower IR intensity, and we are still in the process of fine-tuning these results too. But I wanted, for fairness, to show one here. The phase extracted from perturbation theory and experiment are in really fantastic agreement, even though you can see sort of the actual amplitudes of the sideband aren't the same. And RMT looks like the mirror image of the experiment, and the phase unfortunately doesn't match so well in this side, especially of our sideband. So the whole process is very sensitive on details of the atomic structure, and therefore also the central wavelength of the pulse. So we're trying a few things to improve the positioning of our states in RMT, and if we can't do that, we can maybe change our laser fields slightly so that the correct states become resonant, and hopefully we'll be able to extract a phase which agrees better with the experiment once we finish those calculations. So just to conclude for this project, for the 800 nanometer case, we have great agreement between RMT calculations and experiment and perturbation theory in the continuum only sidebands. However, at our threshold sideband, where we hope to see these atomic structure effects, we do have about a 150 to 200 attosecond difference, possibly due to an inadequate atomic structure description. For 1006.4 nanometers, we have this nice double peak. So this is due to contribution of two states, the 6s and 4d. But trying to extract a meaningful atomic delay in this scenario is going to be complicated, especially because in the RMT results anyway, the two sub-peaks have different oscillatory behaviors. The next project I wanted to tell you about is a different variation on the RABBITT technique called multi-sideband RABBITT. And back in our typical RABBITT picture I showed you earlier, I mentioned how our atomic phase can be broken into two components. So the Wigner phase and phi cc. So the continuum coupling, which arises from the absorption of IR photons. And what we want to try and do with our multi-sideband RABBITT scheme is to try and make some direct measurement, or more like a differential measurement, of this phi cc. So neglecting the Wigner phase, the XUV, or more like compensating for those, so we can extract this on its own. And how we are going to do this is essentially we will have a scheme where our APT harmonics are driven by twice the probe frequency. Or another way to think about it is, if we have a traditional RABBITT scheme, if we half the probe frequency, half the probe wavelength or photon energy, we can now fit 4 photons in between consecutive harmonics rather than 2. So we see the buildup, my color scale is not very good here, of 3 sidebands in between the harmonics, and all 3 of them will oscillate. And this is convenient for extracting phi cc. So if we remember all of our components of the RABBITT phase, there's one from the spectral phase of the attosecond pulse train, but in both scenarios, we're using the same attosecond pulse train. Okay, so that should cancel. There is then the Wigner phase, but again, if we use the same attosecond pulse train and on the same target, that should be the same. So therefore, if we compare the phase from the central sideband in multi-sideband RABBITT with our phase in single sideband RABBITT, we'll be able to look at phi cc on its own when we make the comparison between the two. But first of all, we want to sort of develop our theory if I were going to describe this a little bit better. And we've proposed that we want to treat this delta phi cc, now when we have many IR absorptions and emissions, as a stepwise process. And so they are essentially independent. So we can absorb one, emit one, absorb one, emit one, and treat those in an additive way. So we need to try and do some calculations first to either prove or disprove this decomposition approximation that we will call it. So we want to test the validity of this asymptotic approximation and its extension to 3 sideband RABBITT or even higher order sideband RABBITT schemes. And we're going to do this with single active electron calculations with atomic hydrogen. And even I would not argue that the SAE is of course appropriate to use in calculations with hydrogen because it's only got 1 electron. Next, then, we will compare the measurements from single sideband and 3 sideband RABBITT setups with an argon target. So we'll carry out the experiment and we will also do some RMT calculations to try and separate these CC transitions from the ionization process. So what do we see when we perform our calculations for atomic hydrogen? So there's a lot going on here. In panel B, in the sort of blacked out panel, this is our RABBITT spectrum. In panel A, we've given sort of a line out or an integration over. You can see the main lines in black. We have a lower energy sideband in purple, so that's SL, a central sideband analogous to our single sideband in green, and a higher one in blue, and that's the same for each harmonic group. Down below then, we have plotted the phase extracted from each of these sidebands. And if we took like a line out over one particular sideband, in this case our lowest one, sideband 6, you'll see the nice oscillatory behavior of the sidebands. You will notice that the central sideband is pi radians out of phase with the other 2. This is expected, so our higher and lower sidebands arise from interference of odd parity, so 1 and 3 photon absorption or emissions. The central sideband is always even parity, 2 photons, and that's where that extra factor of pi comes from. And what we can see is as we increase our kinetic energy of our photoelectron, the phase in each of these sidebands becomes closer together. So they all lie on top of each other. And that would lend weight then to our decomposition approximation that these sidebands agree. However, in this low energy region, there is definitely a significant difference between them. So we performed a few more pieces of analysis. We wanted to see if there's any sort of asymmetry between the sideband difference. So we plotted the difference between the central and lower and the upper and central one. And we also compared the phase in the central sideband with an analytical expression from the Dahlstrom paper I mentioned before. And you can see the results are pretty consistent, and that below 10 eV in kinetic energy, we have this discrepancy with the analytical form, and we have this disagreement between the phase extracted from the sidebands. And this kind of difference at low energy has been ascribed to a dependence on phi cc on angular momentum. So the pathway you take is to reach the continuum is important. So if you ionize, say, a 3p electron, you'll have either an S or a D photoelectron, and there could be some differences in the phi cc then resulting from the absorption or emission of an IR photon from those different states. But above 10 eV, we can be quite happy that we can apply this decomposition approximation. So our experimental team at the Max Planck Institute and at Allen University are headed up by Divya Bharti. So she is the PhD student in charge of this project. So it's a heavy weight to bear, keeping us all right. And her PI is Anna Harth. Their experimental setup, again, I can't speak too much about it, but it's this sort of standard one for this kind of pump probe experiment. So there is a harmonic generation stage where we generate our attosecond pulse train from the incoming IR pulse. We have a translational stage to introduce the delay between those. And then we can also add in optics to generate the second harmonic of our IR pulse when we want to change out our probe frequencies. So now that our target system is going to be argon, we specifically want to use RMT and not the single active electron approach for these calculations. And there is a very concrete reason why. So when one has an experimental measurement, you can think of there are many different components that contribute to what we see on the screen. So there's things like detector efficiency. So people might convolve their theoretical results to simulate the broadening one will have with the detector. There's the underlying physics, of course, and one component of that is the photoionization cross-section. And the photoionization cross-section of argon has been very well measured. So the two different sets of points on this graph are from two different experimental results. I've also added the results from two different R matrix calculations. So the black line is from a time-independent R matrix 1 calculation, or you can think of it as being done with an infinitely long pulse. And you can see there's a great agreement here between it and the experimental data. The blue points are for some time-dependent RMT calculations using the same atomic structure description as the time-independent R matrix 1 calculation. And here I've used a finite pulse, and it's unfortunately quite a short pulse, so I could have done a better calculation, but you can see the agreement is still pretty good. If we compare, however, to the photoionization cross-section from a single active electron calculation, we see that there's going to be a bit of a problem. So especially in this region from 15 to 25 eV, so that would correspond in our RABBITT spectrum in argon from about 0 up to 10 or 15 eV, the single active electron cross-section takes a massive dive in this region, where the other experimental and RMT cross-sections are actually quite flat. So we haven't particularly determined if this will affect the RABBITT phase one will extract. However, it will, of course, dampen the height of the peaks, or it will overestimate the first ones, underestimate the higher ones, and that can make our data analysis quite difficult, or comparison anyway with experiment difficult too. So for this reason, to try and get the best comparison with experiment, we are going to use RMT. So Divya has worked very hard in the lab. There are so many things that can go wrong with lasers that I really did not appreciate. So it's a very heroic effort to generate this experimental data for our first 3 sideband results with an argon target. And you can see when she extracts her different phases from her different sidebands, higher, lower, and central one, they look like the figure we showed for the hydrogen results too, complete with the pi phase jump for the central sideband. We also have some quite nice RMT results for this project too. So this is one of our first simulated spectra. Some interesting things you can see in the spectrum too is at the particular energies in our attosecond pulse train, we can actually also ionize the 3s electron in argon. So we have like a 3p spectrum and a 3s spectrum sort of superimposed on top. So this can sometimes make life a little bit difficult here when you can see parts of the 3s spectrum overlap very closely with the 3p. So we'll have to be just a little bit careful in our analysis, but we do see peaks from the 3s in the experimental result. So it's good in a way that we include these as well. At the minute, we are busy trying to accurately estimate our experimental pulse as closely as possible. And one other thing I wanted to point out, which related back to what I said earlier about the applicability of the Wigner delay and also why we would use RMT, is that if you remember back to our photoionization cross-section, at this particular kinetic energy region, in the R matrix 1 results, you might have seen these large spikes pointing down. And these are a series of autoionizing states in argon. They are the 3s, 3p6, and p autoionizing window resonances. And autoionizing states were one of the things he said we wanted to kind of avoid when we calculated something like the Wigner delay, because of the significant reshaping of the wave packet. And here when we have, you can see it's a pulse that's quite broad in energy. We have this nice, quite smooth variation of our different sideband phases. If we use a very narrow pulse, you can see we've become resonant with one of these autoionizing states, and we have a bit of a phase jump here. So I think this is just something, it's nice to show that, you know, if you didn't have a multi-electron code like RMT, your description of these autoionizing states might not be very good. So it's another maybe tick towards using RMT for calculating this kind of thing in argon, but it's also something we might have to be careful about when it comes to the interpretation of our results. So to conclude quickly for this project, I think we've shown for sufficiently large photoelectron energies, where the angular momentum dependence of 5cc is small, we can use our decomposition approximation to help interpret our measured atomic phase in multi-sideband RABBITT. I think RMT calculations are required to study RABBITT schemes, especially with argon targets, and our preliminary experimental and RMT results look promising, but we're still trying to estimate our APT and IR field as closely as possible, just to ensure the most realistic comparison with the actual experiment. Okay, so this is sort of the end of my calculations. And this part is for interested parties and maybe skeptics. So if you're sitting at home thinking, I don't believe the results of any of those calculations, then I welcome you to come and try them for yourself. And you can do so very conveniently through something called the Atomic, Molecular and Optical Sciences Gateway. And the AMOS Gateway project is headed up by our great leader, Barry Schneider at NIST, and Sudhakar Pamadigantam at University of Indiana, who is our cyber infrastructure expert. But the AMOS Gateway involves codes from all over the world, covering lots of different areas in AMO physics. So we have structure codes, we have scattering codes, we have time-dependent codes, both for atoms and molecules. And we also have the band structure code MOL-Hubbard. So these codes are contributed from the US, the UK, from Spain, from Australia. And so we have a very large, very lively group, which meets every other week on a Monday morning or a Monday evening if you're in Australia. And we've ported these codes to this web interface. Here is the link and the QR code if you want to join yourself. I wasn't brave enough to give a live demonstration, but I have this little video instead. So this is the main Gateway's webpage. You can log in with an institutional address. And once you log in, you have this lovely dashboard of all the different applications you can use. RMT is one of them. My video unfortunately shows BSR, which is a different one. And for RMT and BSR, for most of our codes anyway, we have some example inputs. So you will be prompted to pick a particular file, and you can navigate through these directories where we've uploaded the input files for you and start the calculation. So you can also edit the input file in your web browser if you want to. When you scroll to the bottom, you can select which supercomputer you want to run on, how many nodes and for how long, and then launch your job. And you'll be taken to this sort of landing page. You can also, if you want to submit a very long job, you can request email updates as well. So the interface takes care of generating the submission script to the machine scheduler for you. You just have to put the correct input files in the correct box when you're asked. And then in the back end, it will go work away until the job's complete. And then it brings back all your output files for you in your browser. So you can download individual files and you can download a tarball of all your outputs as well. So I think we have 5 or 6 different RMT test cases available for you on the Gateway. So you can have a go, have a look at those. You might want to navigate through the GitHub page first or the CPC to look at the documentation to see a little bit about what you can choose. And so the AMOS Gateway community is very enthusiastic. We're very dedicated. We hope to bring lots of improvements to the interface in the future, including possibly more educational resources so people could try and use the AMOS Gateway during their teaching, during their class. And I also think it's a really great way to bring a bit more equity and accessibility to the AMO community. So people who are maybe at primarily undergraduate institutions or institutions where they feel they're not competitive for funding or for supercomputing time, the AMOS Gateway provides the supercomputing time at the minute, and it provides you the access to these brilliant resources. So just finally, to sum up, I hope during my talk today, I've shown that RMT can be used to study a wide range of AMO problems, but most specifically, single photon ionization in atoms. Just as another point, the code is efficient and it can be run on thousands of processors. So we can scale to even larger calculations. I think our early comparison with our 2 different sets of experimental results are very promising, and we look forward to even improving that comparison further. And again, the best point about RMT is obviously the people. And because it's an open access code with such strong developer and HPC consortia support, it would be really great if more people could become users of the code. So finally, a big thank you for your attention. Thank you again to the Atto Fridays organization group for inviting me along to speak. I thank you to all our funders, universities, funding agencies, HPC consortia and centres. And a special thanks, I told my mom I'd make our cats famous. So a special thanks to Mr. B, my 15-year-old one-eyed cat, Muffin, I think she's 9 years old, three-legged cat, Jean, who's my nephew. He was adopted by my brother and sister-in-law, Mitty, who he's got an interesting personality, and Bill, who was a feral cat when I arrived home at Christmas, but over 5 weeks, he has become a house cat. And now he just hangs around with my mom and dad all day. He's a real old man. And then finally, any questions? So if you want to contact me at the minute, after this talk, my address at the minute is kathryn.hamilton@direct.edu. That will probably change in a couple of months, but I'm sure you can find me online. Thank you.
Thank you so much for this really, really nice talk. I see there are some questions coming. So do type your questions in the Q&A tab. So let's go for the questions. The first one is from Andrew Brown. For the below threshold RABBITT, how do you calculate the photoelectron momenta? Projecting onto plane waves that close to the threshold is probably unreliable. So are you projecting onto Coulomb waves?
Yes, so this is one of the things we have also considered when we don't have such a good agreement with our threshold sideband phase. So indeed, at the minute, we are projecting on the plane waves. So there is a significant field-free propagation time at the end of the calculation. But of course, when you have ionization from a neutral system, it would be much more correct to project onto Coulomb waves. So this is an improvement or another thing we are considering implementing to try and hammer down where this difference between our RMT and our experimental phases.
So Andrew, if you want to follow up, you can.
Yeah. So we've been doing this. So we have code that can do it. So if you want to talk about that, we can.
Brilliant.
Well, I say we have code. Luke has written some code to do it. I'm now sharing Luke's.
I was going to say Luke beat you to it because he messaged me pretty much this exact question a couple of days ago.
Yeah, he just messaged me offline saying, "Yeah, well, you just stole my question, so I'm sorry."
Yeah.
But we should talk about that. That would be nice.
Definitely.
Cool.
Pascal Salier, thanks, Kathryn, for the nice talk.
Thank you, Pascal. Thank you.
And he has a question on below RABBITT.
Yeah,
okay.
No problem.
We're gonna you have already been unmuted. Very good. Thanks for the team.
Okay, can you hear me?
Yes, we can hear you.
Okay, thanks, Kathryn. I have a question on this below threshold harmonic results that you showed in neon. I mean, we made the measurement recently in helium. And we can clearly see if we cover the whole resonance with the exciting harmonic, we can measure a full pi evolution inside the sideband, which does not appear in the results that you showed, neither in the experiments nor in the theory. So I was wondering whether this is due to the narrower harmonic bandwidth that would sample only part of this phase jump, or whether this is something more physical due to the difference between neon and helium.
Yeah, that's a great question. So I would have suggested your first suggestion as well. So there's a very strong dependence on how the laser parameters, in a sense, fit in with the atomic structure. And we can see this with I think the disagreement, especially between RMT and the experiment for this threshold where we had for the sideband where we had the 2 peaks. It's clear that if you don't cover the entire, say, width of that state in energy, you don't extract the correct phase. So I would naively say it would be the former problem, in that potentially our pulse is too narrow to cover the entire width of the state, and that's why there's this energy difference. So yes, I see there's been a lot of very recent work. I apologize for not including your work in the presentation at the minute. So it'll be very interesting to compare that with what we currently have and see the differences, see if we can make any improvements.
Mm-hmm. Yeah, thank you, Kathryn. Also, maybe a technical question. So in your results, you integrate angularly, and the other question is, how do you take into account the spectral resolution of the spectrometer? Do you have to do that, or?
Yes. So in RMT, we can calculate our photoelectron momenta at every angular slice, not to 360 degrees. So I pass those along to Matteo, and he knows the angular acceptance of his detector. So the RMT results are integrated only over that particular angular range. Things like detector efficiency and stuff like that, rather than angular acceptance, we haven't done anything yet to, say, convolve or broaden our RMT results to match more closely the experimental ones. The experimentalists were very great at estimating what their incoming laser field, what their electric field was. So they very nicely give that to us in a file, which we can read in. So we're pretty confident we're using the correct incoming field. And then, yes, like you said, we could do things then to more accurately simulate what the experimentalists see on their results screen too. But the angular acceptance is taken into account, and that is the range that's integrated over for the RMT results.
Thanks very much.
Thanks.
We would like to thank the speaker, Dr. Kathryn Hamilton, and all of you who are watching on YouTube. Thank you so much. See you in 2 weeks, and take good care of yourselves. Okay?
Bye,
Cheers.
everyone.